Okay, so sorry for the delay, but eventually we were able to start. So our last lecture, which was yesterday, what we did was to derive the expression of Lagrange equation. And basically, we were able to evaluate the pros in terms of easiness of resolution of an exercise, of an example that we previously tried to study resorting to the D'Alembert's equation. And we saw that in terms of time, it was much, much faster and easier because eventually through the definition of kinetic energy, we were able to derive the equations of motion for the system just through basically a series of derivations. So if we want to recap, we could write that. So generally speaking, what we're going to do today is to see how we will be able to include the constraint equations within our Lagrange equations. Okay, so yesterday we studied an example in which the set of Lagrange of, let's say, generalized parameters was the minimum set already that we needed to describe the system, meaning that they were already compliant with the constraints associated to there was a hinge and a tray in the system. This is not always possible. This is also to answer to some of you who asked, okay, but what if we are not able to properly select generalized parameters so that all the constraints are automatically satisfied? That can be the case of a complex system in which the choice of the most adapt set of generalized parameters is not obvious. Okay, so what do we do in those cases? What do we do if not all of the constraints of the generalized parameters that we choose are independent? Well, in that case, we have to include the constraint equation into our equation of motion. Okay, this is what we have to do. Unfortunately, there are cases in which this is easier and cases in which this is less easy, depending on the nature of the constraints. And in fact, these two cases correspond to the analysis of holonomic or non-holonomic constraints. The former are much easier to encompass in Lagrange equation, the latter not so much. And this is what we're going to see today. So we're going to see how to include constraint equation, holonomic and non-holonomic constraint in Lagrange equations. Okay, so this is, we could, let's say, entitle this lecture as inclusion of constraint equation into Lagrange equations. Would you mind if I keep one of the doors open so that we have? Oh, okay. I appreciate it. All right. So just to recap, we had that D'Alembert's equation read like this. So we had a weak formulation. We have a weak formulation that we can call like this. Which we wrote like so. So the vector of the generalized forces equal to 0. And then, through the hypothesis of linear independence of the Q, we got a strong formulation, okay? That's to say, very straightforwardly, Q equal to 0, like so. The same we did for the D'Alembert-Lagrange equation, okay? So we have here the D'Alembert-Lagrange equation. Which we wrote like this. Yeah. Okay. And through the hypothesis of linear independence, we had what we call Lagrange equation, like in a more proper form. All right, so in this case, I'm writing the form in which we only have kinetic energy and not the Lagrangian function. Okay. All right. So these were basically the results that we had yesterday. Now, let's try to introduce the constraint equation into this formulation. Okay? Okay. So let's introduce constraint equations into my Lagrange equations. In this case, we have two possible ways to do it, depending on the nature of the constraints that we want to include in our Lagrange equation. So the first one is called embedded formulation. All right. And already the name gives you a flavor of what we are talking about. Embed, meaning include, and actually through a substitution operation. So this is the first technique. What are the hypotheses upon which we will derive this formulation? We have three hypotheses. First, the constraints have to be holonomic. Okay, so they have to have this form here. C of Q and time equal to 0. Okay, you can call them, if you want, kinematic integrable or geometric. Then second hypothesis. We have a series of constraint equations through which we will be able to describe the dependent generalized coordinates as a function of the independent coordinates. So these are via the constraint equations. Okay. So the constraint equations are those equations, typical algebraic equations, that relate dependent and independent. So the dependent, by their name, by definition, can be derived through the constraints starting from the set of the independent ones. Basically, the third, well, I would say this is not really an hypothesis. This is like a result. We have that in turn, what we get is a system of differential equation in the Qs. So we can say that we get a system of differential equation in the Qi. This is what we get eventually through this so-called embedded formulation. Then there is the second method, which is called augmented formulation. All right, augmented. Let's see what are the hypotheses for this. So the hypotheses are that you can both treat holonomic and non-holonomic constraints with this method. Okay. So both holonomic and non-holonomic constraint. Possible. And we know that this means basically that they can have either this form, as we have just written, or this form. Okay. And the second, say, important aspect is that contact forces and constraint forces, typically contact forces, appear in the system. Okay, so if you remember yesterday formulation of Lagrange equation, we did not write contact forces in our formulation because they were workless. We were making the hypothesis of having workless constraints. So the contact forces, which are typically the forces exerted by constraints, contact, they limit motion and configuration through contact forces. They didn't appear. Now here we will see that they have to appear in the formulation. So constraint forces do appear in the formulation or in the equation, if you want. As a result, lastly, we get a system of a mixed system, we will see, a mixed system of linear, let's say, differential equations and algebraic equations. Okay, and this is the main difference. So we get a system of both algebraic and differential equations. Of course, the differential equations are the equations of motion. Algebraic equations are the one represented by constraints equations. Okay? Okay, so let's start from the first one. Embedded formulation. We assume to write it using the Lagrangian function. So L, which is equal to okay, is the kinetic energy minus the potential energy. We perform the partition of the coordinates. This means that our Q, the column vector of generalized coordinates, becomes Qi, and then you have a Qd, okay, transposed. So let's rewrite my D'Alembert-Lagrange equation using this partition. Okay. Well, we just have to partition it. So first we have the derivative with respect to the independent coordinates, and then the dependent ones. And then we have the second part. It's not T, it's L. Now, you see, I just rewrote the D'Alembert-Lagrange equation, partitioning between independent and dependent. This, which is a vector, is the portion of the non-conservative external forces associated to independent coordinates. Okay. So here, if you want, we could also write Q non-conservative external equal to Q external non-conservative transpose I, and then you have Q D, non-conservative transposed, all of this transposed. Okay, just following the same partition. Okay. Now, oops, we have that for holonomic constraints, and here, remember that we are dealing with holonomic constraints. For holonomic constraints, that delta QD is equal to C Q di delta Qi. Did you remember this? Huh? We derived this from the Jacobian of the system. Now we can make use of it and substitute it in here. Okay? But if this is true, we also have another implication, which is the following. If our Lagrangian function is typically, as we have said before, a function of the Q dot, and time, well, if this is true, if we have this relationship between independent and dependent coordinates, then this dependence can also be written as such. No? It means that if the dependent coordinates can be written in terms of the independent ones, then the functional dependence of this Lagrangian function, there is an I here, it can be rewritten like that, no? Is this clear? Through this. Okay, is this clear? Huh? I mean, here I'm actually saying that L depends on all coordinates, generalized coordinates, but the dependent coordinates depend, by definition, on the independent, so the functional dependency of L actually holds only, can be reduced to only the independent ones, okay? And this is a very important fact. Why? Because it means that if this is true, then this and this are 0. Okay? All right. So we can say that since L depends only, or if you want, can be recast so that only its dependence on the Qi and Qi dot is present, we have that dl over dqd dot is equal to dl over dqd, and this is equal to 0. Okay? If we want to be correct. And so it follows that the following holds. Sorry, it's not the total derivative, it's the partial derivative. Okay, you see, the only thing which is left from the previous, from the dependent part, is the one associated to non-conservative forces. Okay, and then of course all the rest is still in here, in L. Okay, so this is the only part that survives of the second term before. Super. All right. In fact, all of this if you want, can be recast. Actually, let's write it on top, otherwise we will have issues of space. So these two terms can be grouped into a new vector by definition, which we call QE non-conservative transposed B. Okay? And so eventually our equation becomes like so. D over the T, very simple. dl over the Qi dot minus dl over the Qi minus Q and C EB transposed equal to 0. All right. Now, it's evident what we're going to do now. Since we are only left with the independent coordinates, well, we know what we can do when they are independent. We can get rid of it and pass from the D'Alembert-Lagrange form of this equation to the Lagrange form. Okay, because we are left only with independent ones. So if this is true, then also imposing the first of the two factor equal to 0 is true, because the Qi are all independent. Okay, and then we are left with the usual form of Lagrange equations, and you can see that we see basically nowhere formally the presence of constraint equations. These here are all linear independent. Okay. So, since the Qi are independent by definition, you can write And please note that we can write if and only if. So okay. And this is, again, the form, the simple form that we started with in the very first slide of the lecture. If you remember, it's formally very similar, but in this case, it is only written in terms of the independent ones, because we have included, namely we have embedded inside the equation of the dynamics of the system, the constraint equations. Okay? And that's why it's called embedded formulation. So everything is very easy here. So again, to answer to the question, what if we do not set the most appropriate set of generalized coordinates so that all the constraint equations are satisfied? Well, we can do this. We select the minimum set of coordinates that we need to describe the system. We partition between dependent and independent. We express the dependent in terms of the independent via the constraints, and then we insert them in there. If you think about it, what we did yesterday during our last example is writing this exact equation where we already selected the I, the independent ones. So the two that we selected, so the angle and the Q, the sliding coordinate of the mass, were already the only independent ones. Okay, and this was 0, basically. So we arrived there via an appropriate choice of let's say, of the generalized coordinates. But this cannot always be done if the constraints are non-holonomic. And this is why we are going to see now the augmented formulation. Okay, again, this works for holonomic constraint equation, in which, remember that we have this form, which can, in turn, be written as such. So dc over the q times the q over the t plus the c over the t equal to 0. And therefore, b q dot of t plus a0 is equal to 0. Okay? This is basically via differentiation. Actually, this is total derivative. You can write it like this if you want. Okay. Or otherwise, we have non-holonomic constraint equation. And therefore, we have C of Q, Q dot, and T. And this, already we have C, can come directly in the form that we have just written. So you see, this is kinematic non-integrable. These are kinematic integrable and geometric, okay, as you have said. Eventually both, so that's why this method works for them both, because both of these constraint types can be put into this form. Okay. In which basically you do not need, neither you have, the straightforward relationship between independent and dependent coordinates. So in this case, what I'm saying is that for non-holonomic constraint equation, you cannot write this. Okay? This, which simplified our lives before, cannot be written now. We don't have it here. Now, let's see the consequences of one hypothesis. So for work-less constraints, we had the following. Delta WC is equal to 0, and therefore we can write that QPC times delta Q is equal to 0. Okay, so this is the vector of contact forces, generalized contact forces. Okay, so this is the vector of generalized contact forces. Right? From here, it's either QC is 0, as we have said, but this is, let's say, the trivial case, or they are perpendicular. We also have another thing to say, that if you remember the Jacobian of the system, which is CQ, which by definition could be written as the derivative, the partial derivative of C with respect to the Q, is by definition. From here, it means that each of the column of this Jacobian is perpendicular to the dq, okay, to the vector of the generalized parameters. Is this true? Is this clear? Huh? when you perform the derivation, okay, the derivative operation of a vector with respect to another vector, the column of the matrix which results from this operation are perpendicular with respect to the vector upon which you perform the derivative, okay? So each column of CQ is perpendicular to the Q, okay? So this must be perpendicular to the Q. This is also, actually, we could write like this, to the D, let's say, Q. It is pretty much the same, but let's keep it like this. So we have to express a vector of contact forces which is perpendicular to the delta Q. And we also already have encountered a mathematical object whose columns are perpendicular to the same very object. So always the Q. So what we can say is that, for example, we can assume, and we can make this assumption, that this vector of generalized contact forces is nothing that different than the column of this CQ times a multiplying constant, okay? Because they have the same direction of this. So we can say that they are exactly those columns with the multiplying coefficient, okay? So we say without loss of generality, we can set that QC, the vector of generalized coordinates associated, the vector of contact forces, sorry, can be equal to minus, and this minus is only due to conventional reasons, is CQ transpose our Jacobian applied over a vector lambda, which is called vector of, have you ever encountered this? Lagrange multipliers. This is by definition. Then, and so you can see that Lagrange already taught about this problem of non-holonomic constraints not being, encompassed directly, embedded directly into Lagrange equation. So we had this other formulation. So since in any case, our constraints are worthless, we have the QC perpendicular to delta Q, and therefore minus CQ transposed over lambda is perpendicular to delta Q. Okay? So it means, eventually, that minus CQ transposed, applied over lambda, all of this being transposed and applied over delta Q, this is 0, okay? This is, I would say, pretty obvious. So what we can do here is to add this quantity, which is 0, to our previous Lagrange equation. So it's a 0 quantity. We are just adding a 0 quantity. This is a null quantity. And therefore, we get the following. All right. This is CQI. Okay. So what I did was just to rewrite the same equation, but including these two parts here. So this part here is just minus QCI, and this is minus QCD. Okay. Now I make use of the fact of having introduced my Lagrange multipliers. So, can I slide? All right. I assume that my lambdas, so my Lagrange multipliers, are such that the T of dl over dqd dot minus dl over dq d minus q plus lambda c q d is equal to 0. Okay? So what I'm saying here is that I choose my Lagrange multiplier so that this equation here is satisfied. Hmm? So I choose my lambdas so that these equations are satisfied. And therefore, my previous equation reduced to what? It reduces to the following. You see? But now we are in a rather good condition because in this case we can still pass from this weak formulation to the strong formulation because here we are only left with independent coordinates. And so if this is true, only and if and only if the following is true. Okay? So we have this, which is our assumption. And then we have this, which is our equation, the final form. So let's put everything back together, and let's see what happens. So summing up, we have Okay? And this is because of, by definition of the lambdas. We define the lambda so that this is satisfied. Then we have, what else? We have what we have just derived. That's to say this. Bless. Okay, and this is what we get. And plus, we have what? We do not have to forget the constraint equations. We also have the constraint equations. Okay? So this is by definition of the lambda. And these are our constraint equations. Which I wrote in this form because they are holonomic or non-holonomic. Well, you can see that now I can use the partition in the reverse form. Okay? So if I can rewrite, you see, the first and the second equation are formally identical, apart from the d and I subscript. So if I rewrite everything back in the Q, I can get only one equation. Okay? So let's rewrite it. So I can use the partition definition so that I can finally write my resulting system of equation, which is the following. Huh? And this is the final form of the embedded formulation. So what are the differences here between the result of the augmented formulation that we saw previously and this one? Can you name the difference? Can you spot the differences? The Jacobian, okay. So we can say that here the set of unknown has been incremented, no? Because we have not only the Q, and so the Qi and the Qd, but we also have the lambda. So unknowns. we have the QI, which were the ones we had previously. We also have the QD. And then we have also the lambda. So you see that we have quite a disadvantage in doing so. Plus, there is also another thing, that we have this set of equations here, okay, which are the constraint equations. So while previously we had, and these typically are algebraic equations, we have seen it typically. So eventually, while previously we had, as we have already anticipated, a system of differential equations, here we have differential and algebraic equations. We have a mixed system of both. What are the consequences of this? Higher number of unknowns, large computational time required to solve them, higher complexity in terms of nonlinearity, and so possibilities of singularities when solving them. And in general, a less simple and immediate description of the system and its evolution. Okay. So, as you can see, unfortunately, there is a reason for distinguishing between holonomic and non-holonomic constraints, because not only their physical meaning is different, one constraining the configuration, the other constraining the motion of the system, but also the mathematical treatment that follows is completely different. Okay? So you can set it here now. This is a mixed system of algebraic differential equation. Now, we could already start eventually the treatment of what is called Kane method, because Kane method tries to overcome these difficulties. Okay, because eventually it relates on one observation. Either if your constraint is holonomic or non-holonomic, you can both write them in terms of like this, okay? Because you can always derive, as we have said, in the kinematical form. We can always write them in the kinematical form, either if they are integrable or not. And the idea of Kane is to write the constraint equations not just in terms of generalized coordinates, but in terms of their velocities. Okay, so that they can always be included in the kinematic form of the equations of the constraint equations. Okay, bypassing this problem here, because if you remember, when we were, let's say, deriving the embedded formulation that we had here, sorry. We relied on this fact here to write the embedded formulation. This cannot be used in the non-holonomic case. Well, instead of relating, we will see, let's say, the order 0 of the function, we will relate the velocities. And this then can be used both for non-holonomic and holonomic constraints. Okay. We could start it already today, but I prefer to start it on Monday, because otherwise I think we can get confused a little bit, because the formulation of Keynes equation requires a little bit more focus. And so I think it's best to treat it separately and not all together with the embedded and the augmented one. Okay? So we stop here a few minutes before the end of the lecture, let's say 10 minutes before. I'm available for questions, if any, or issues, or whatever question you have. Okay? Mm-hmm. Che c'è che non la convince? Qui? Questo? Ok. Allora, rispondo in inglese. So here we have two facts. First, our constraints are worthless because we are making this hypothesis for simplifying reasons. If the constraints are worthless, then the contact forces, which are typically the way constraints enter the equations. If you think about a fixed constraint, you can have contact between, for example, a cantilever beam and the wall. Or, for example, in a hinge, you're going to have contact forces between, I don't know, the end of your structure and the hinge itself. Well, if this is true, then you have that this product, which is exactly the definition using D'Alembert's equation of this work, virtual work, is zero. If this is zero, you have two possibilities. Either this is zero, the generalized contact forces are zero, but this is the trivial case, we don't consider it, or the two are perpendicular. Okay, so this is the first observation. Second observation, we have defined for different reasons the Jacobian of the system, like this. Now, when you define a Jacobian like this, it's a mathematical property that you can demonstrate, but even intuitively, you can already think about it, that the columns of this matrix that you define through this operation are orthogonal to the vector upon which you perform the derivative. Okay? So each column of this is perpendicular to the Q. Okay? Now, and this is what you get, actually, in this case, of the delta Q of the variation. Okay? So you have these two facts, this one and this one, you see? So if CQ is perpendicular to delta Q, and QC and CQ are both perpendicular to delta Q, means that these two must be parallel. Okay? In fact, here, so it should be like this. So each of the column of the CQ is not the matrix. It's not the overall matrix. If you really want to be formally correct, you should write it like this: CQ, whatever, K. So each column is the column of CQ. So it means that each column of this column and CQ must be parallel. All right? If this is true, then I write that CQ, I assume them to be basically defined as CQ applied over a vector of lambda. So when I do this operation, it's like if I'm actually multiplying each column of CQ with a scalar. Okay? That is exactly equaling to say that CQ is basically parallel to each column of this. Okay? All right? And this is the way I define Lagrange multipliers. Why do I introduce an additional set of unknowns? Because this way I will define the lambda so that the second part can be set equal to 0, because this is, before of this, in the embedded formulation, I get rid of this just resorting to the relationship that we have between dependent and independent coordinates through the Jacobian. But in this case, I cannot do it. So how do I get rid of this part and be left only with this? Introducing a new set of unknown so that this part is automatically satisfied. So once this is done, I'm left with this. So this is the definition of the lambda. This is the equation that defines the lambda. I'm left only with this. These are independent. So I can pass from the weak formulation to the strong formulation. QED here. I just put it here. It's the same. I just put them in the same form so that the formal identity of these two equations could be evident. Okay? So using the partition, then you set them, you put them back together. So it's a kind of, if you think about it, it's kind of an elegant way of doing it, because you first separate it and put it back. But still you are left with this and with a lot of unknowns. So this and this. And if you want to know, this is the way Adams and most of softwares take all constraint equations. Why? Because, as I told you, this is general. It works for every kind of constraint. All right? But this explodes the dimensionality of the problem. So the dimension of the matrices involved in the resolution of this equation becomes super high. Now we have, the necessary calculation power for our computer that enables us to treat them quite easily, at least for some problems. But back in the days, this could be a problem. Okay. And again, if you want to know, another thing that is important, Adams and other softwares typically resolve your equation of motion resorting to Lagrange equations. Okay, so really using this embedded formulation. Even if from, let's say, a practical standpoint, and we will see it next week, Keynes equations are the most efficient way of deriving the equation. Why? Because, and we will see again, redoing again the same example over and over again with Keynes equation for comparison reason. You have a, how to say that? You have a principled and structured and well-defined way to derive the equations of motion, but so that you avoid a lot of mechanical operations which are involved with this, because here there is a lot of derivation to do. In Keynes equation, we will see it's not necessary. But in computers, we know that mechanical operations like the one involved here are typically welcome, because you can do it with a routine. But if you want to analyze the dynamics of a system as a designer, and you want to have an idea of how a system moves, Keynes equation is the best way to go. We'll see tomorrow, actually on Monday. Okay? That's it.